Right. So I'm Vangelis. I'm an Atlas collaborator, and today I'm gonna pick it up from where the guys gave these nice introductions. So what you're gonna see in this presentation, it's actually an implementation of some very common feats we do in Atlas, and especially in the supersymmetry searches, using pyhf and cabinetry libraries. I don't need to talk a lot about introduction to these things because we spent the last hour having some examples. So I will go directly to what I have done there. So this notebook is a little bit extensive and self-explanatory. I try to put it there as a future reference as well, so people can go back and read all of these things. Now I have 20 minutes, so I'm not gonna read all the single lines. So I'll try to give you the big picture. There might be details on coding implementations, and again, maybe I can skip a little bit of these things. Maybe, of course, we can discuss whenever you want, but let's try to see the big thing here. So this is inspired from Atlas supersymmetry analysis, and a common problem we have there is that we need to estimate the backgrounds, right? The standard model backgrounds. And then we need to do some interpretations in a way that if we do not have a data access, we can place exclusion limits, either model dependent or model independent. If we have a data access, we can measure signal strength, right? And to do this in SUSY, in Atlas SUSY things, we use three types of fits, which is what I quote there. One is called background only fit, which is the main fit that helps you extract the background model from data. And then there is what's called exclusion fit, which helps you put model dependent exclusion limits. So a particular SUSY model, is this excluded or not? And then what is called the third one, discovery fit, which help us to place model independent limits. In terms of some generic, let's say, BSM model that can contribute events to the signal ranges. So, these are types of fits that have been introduced by the HistFitter package, and this is based. It's a fitting framework that is based on HistFactory, RootStats, and these are root-based implementations. So what we're gonna show today is this type of three fits only implemented only using the Python libraries pyhf and cabinetry, right? So that's the point of this contribution. So I have a section that I describe a little bit how an analysis is designed, which again is kind of a pedagogical introduction. Maybe I will just go directly to this illustration that can help us to describe what I want. So a common supersymmetry analysis, at least on Atlas, and I think on CMS as well, it's defining some kinematic regions. And actually the whole analysis is driven by the definition of what we call signal regions, right? The blue boxes here. So these are regions of the phase space that we can discriminate signal from backgrounds, and usually it's maybe very energetic regions and with some characteristics that the signal has and so on, right? But what we want to do is estimate the standard model background in these regions. And we do this by using what we call control regions. So these are auxiliary regions of our measurement that are dominated by backgrounds, and we can use them to estimate the backgrounds. And what I mean estimate, I have a little discussion before about reducible and irreducible backgrounds, and probably you have heard these terms before. So I'm going to focus here on the irreducible backgrounds, which is standard model, let's say, processes that they have the same signal characteristics, the same characteristics as the signal. And what we're going to do in this kind of approach is estimate these backgrounds with what we call semi-data-driven way. So in the signal regions, I can take the shape of the distributions from Monte Carlo, and I can extract the normalization from the data, right? And this is, I use some information from Monte Carlo for shapes, but I use the data to control the normalization of the backgrounds. And then I can have some validation regions in between to validate this data model I extract. And this is the whole, idea. I have signal regions where I target my signal, control regions, the background, and intermediate, I have the validation regions. So, and all of this is happening statistically with a bin likelihood fit, and which has a very general, this kind of term. It has some Poisson terms to describe the yields in the different bins, and which is controlled from some normalization factors, of course. You can control the backgrounds of the signal that contribute to this yield. And this yield can be in the signal regions or control regions. And then you have another term. This is a Gaussian term, which controls the nuisance parameters of the fit, which represent the systematic uncertainties, and we can constrain or change a little bit the value. But this is the general, picture of the likelihood that we'll try to minimize or maximize to extract the parameters of the fit, right? That we care, which is this normalization factors. And all of this is based on an example analysis. So we built a toy analysis a few months ago to do a tutorial, and I use this data to come here and make this notebook as well. It's, it's trying to explore this hypothetical SUSY model, which you have a very rich final state, quarks, jets, flavor jets, photon, tau leptons, and missing energy from these red particles. So it's very rich final state. And then we constructed some example toy signal controller validation regions to just get the example going, right? These are not important here, but I put it for reference. So I'll go now to, talk to you a little bit about these three different fits and how these are implemented by using pyhf and cabinetry. Of course, you need to do some imports, as always. And in this, I think Alex talked before about what is a configuration file, and I have it here on the side. That's why I can drag it up a little bit. That's why I opened it like this. So in this configuration, this cabinetry configuration file, I have defined my signal validation control regions with some selection, and this is single bin regions, as you see. So we have one bin signal region, one bin validation TT. Y, one being validation WY. These are two different backgrounds. Yeah, this maybe I skipped this part. I will consider like one signal and two backgrounds, right? Top production with a photon and W production with a photon. And then I construct control regions that target these backgrounds and validation regions to validate these backgrounds and the signal region. I define everything in this configuration file, along with my samples, and a dummy systematic uncertainty. This is just a 20% flat uncertainty as a normalization type, just gonna affect the normalization of the signal. And of course, then I need some parameters of the fit that I'm gonna fit here. Here you don't see any signal parameter, right? Because this is a background only fit. I'm gonna use this fit to extract the background module. So this is what the configuration file looks like. So I'll go back to the notebook, and you can load this configuration file, and gonna tell you like you have 3 samples, 5 regions, blah, blah, blah. And then of course you need to build, I think we touched these points as well. You need to build some histograms from root files. This I have done already, and I provide you the histograms, so we don't need to run this line. We can directly run maybe I could actually run the notebook while I'm going, right? That would be nice. Wait, now I need to figure out how to clean this thing, clean all outputs. Yes. Yeah. So I load the configuration file, and I have the histograms, so I can build the histograms. And then what I can just do, I can do some inspection, right? I can see a little bit what I built there and what I have loaded to my workspace. And one thing I'm using here that it's quite often that we do, it's to use some data blinding, because In realistic scenarios, you don't want to open the data in your signal regions immediately. First, you want to be sure that you do a nice background estimation. So I wrote a helper function. I provide a lot of these helper functions in the tools.py. So you will see now that I have kind of blinded the data, and the data in the signal region is just the number of Monte Carlo without any significant digits, right? And this is a way to inspect a little bit what I have loaded into the workspace. Then I will go and I have some uncertainties, which include statistics and this flat systematic component. And then I will go and do what I call this background only fit. And this background only fit is using information only from the control regions, right? That's an important bit as well. I want to take out validation and signal regions for a little bit. I want to only consider the control regions and extract the normalization factors only there, and then extrapolate them over to the rest of the regions. That's why I'm using this .prune utility of pyhf, which is taking out, this is going to take out channels from the workspace, and then I can get something like a pruned model, a reduced model, which is only includes control regions, right? So I can run this this cell. It doesn't show so clearly here that I took out signal and validation regions, but trust me, I did. And then I can fit this likelihood only in the control regions, and I can visualize the result. So you will see here that I extracted two of these normalization factors that I defined here, right? I defined on my configuration file. So I can have a nice visualization of what is the values of these things. But of course, I want to see the impact of the result of this fit in the signal and validation region, so I can put this back. And the important thing to put them back is this cabinetry function, which is called match fit results. This is what you need to use to put this back. And I'm still gonna keep some blinding, because what I'm gonna do with this cell, I wanna validate my model in the validation region. So I'm gonna run it, and you will see now, you will see that the data in the signal region is still blinded. You see just 9, which is just a number. And you will see the agreement on the validation region, which is okay, which is fine, right? 1.5 sigma. So, okay, let's assume that this is fine for a validation region, for a validation of the background model. So we can look at the data in the signal region, and you will see that you will see some, if you reveal the data, this is number 15, the fitted is 9.6, so you get something like 1.5 sigma of an excess. All of these are mock data, toy data, right? Just to make the example. So this is the result of what we call background only fit, being able to extract the model in the control regions and extrapolate to signal and validation regions. And then another useful thing that we usually do is to get an uncertainties breakdown. So how much the uncertainties affect the yields in these different regions. And for example, I have written some helper again functions to do these things. And you can see, for example, for the signal region, that this flat systematic uncertainty I put there, it contributes to like 20% of the uncertainty of the region, right? This is the point. And this is the first part, right? The background on the fit. So now that we have extracted our background, maybe we can do this exclusion, right? We do not see a data excess. So we can use this data to see which SUSY models can be excluded, which are still surviving, and so on. So there is a little bit of statistics introduction to how we do these things. Now we're gonna build actually a background plus signal likelihood. So this likelihood is gonna have both signal and background terms, and we're gonna test the background plus signal hypothesis against the background only, right? So the question I will try to ask with this hypothesis test is, can I exclude the background plus signal, or is it surviving? And to do this thing, we're gonna use the CLS technique, which is something like a p-value. We construct a test statistics based on the likelihood profile, likelihood ratio, profile likelihood ratio. And then instead of p-value, we use the CLS value. It's not exactly the same. It's similar to what we all know as a p-value. But anyways, here I have built another configuration file, which at this time includes Wait, I lost a little bit my lines. Yes, I have built another configuration file, which at this time includes a signal. So you will see here, it's the same. Yeah, it's signal and control regions. I don't know, I don't need validation regions at this time, right? I validate my background. And the difference is that now I include a signal sample, and also I include the normalization factor for this signal, right? That is the difference with previously. So I'm gonna load this configuration file, and then I'm gonna build a workspace again, and I can have a brief look inside the workspace, and you can see now that in all my control and signal regions, I have this signal sample beyond the backgrounds. And then there is a trick here that I need to explain. So usually we have two kinds of limits. We have what we call the expected limit and what we call observed limit. So the difference is that for the expected, we use Monte Carlo prediction, not real data, while for the observed, we use real data. So what I'm gonna do here is do again a background only fit and use the result of the background only fit as observations, right? And I'm gonna again, remove I'm gonna remove the signal from the workspace and get the background only model and data and fit this thing, fit this model. And then, okay, no, sorry, here I'm fitting this model and I'm getting the normalization factors of the background, of course. And then I'm gonna use this result of the background only fit to construct something like a toy or a Asimov data set that I'm gonna use as observations, right, instead of real data. And this is how we're getting what we call expected limits. And then here it's in this block, it's the main thing. I think you need to focus, in this and this. So first, I'm gonna calculate the expected CLS values with using this pyhf hypo test. And what I'm doing here is I'm fixing, this is a value of the signal normalization factor that I want to fix to 1, and then ask pyhf what is the CLS value we can get from there. And I'm using this Asimov data set. I'm using Monte Carlo post-fit. While for my observed, I do the same thing, but I use real data, right? And then I can run the cell, and you can get this CLS, either expected CLS with the uncertainties ±1, or you can get the observed CLS. And then the question we always ask is if this observed CLS is below 0.05, so then we can say we can exclude this model. And as you see, this is kind of an excluded model. This it's very small value of CLS observed. But this was for a signal model, for a single model. But usually when we get these plots that maybe you have seen before, we have CLS values for multiple points. So I have a kind of a bonus here, how you can loop this procedure and to calculate CLS for multiple points, and then you can interpolate. Probably I'm not gonna go through because I don't have time, but the code is there. I think maybe one thing I want to touch here that is using a very combined large workspace, configuration finder workspace. So I think this is something this is something we talked before, that I can take a single configuration file, and I can put there a lot of samples. I can put multiple signal samples, and each of these signal sample will have its own normalization factor. And then what I can do on my fitting is that I can do this fix and calculate. I can fix all the normalization factors of the signal except of one. And for this one, I will run the fit and I will calculate CLS. And then I will loop this procedure to fix another normalization factor to 0, keep varying another normalization factor and fix the rest. So I'm always keeping one alive and killing the rest, let's put it like this. And I have I also put that can take a little bit, but you can very easily parallelize this with Python multiprocessing. Let's say if you have a machine with a lot of CPUs, you can run this parallel loop, and you can get a lot of results quickly and put it in a. Maybe I can just run this quickly to show you. It's going to take very quick. And then I can put the results in the data frame, and you'll see that now that I have a CLS values. It says p-value, it's not p-value again, it's a CLS value, and it changed this for different SUSY models. And you can kind of put all of this in a plot heat map that would say these are excluded, these are not excluded. Okay, final thing I'm going to touch is the discovery fit. This is what we use to place model independent limits. So in terms of generic BSM events that can contribute to the signal region, or we can translate this to upper limit on cross-section of a generic BSM model and so on. So the setup of this is very similar to the exclusion fit. And if you see the configuration file is very similar to the exclusion fit for a single model. It has one signal model and one normalization factor. So I can load this thing, but what I want to do here is convert this real signal to a dummy signal. And I have some explanation. Yeah, I will make, I made already a workspace, and this workspace includes a real SUSY signal. But what I want to do is convert it to a kind of a dummy signal that gives me one event in the signal region, 0 events in the control region. And then I have a kind of one-to-one, how's it called? Between the normalization factor and the signal yield, because I have normalization factor of 1, giving me 1 event. So as I change the normalization factor, I have a direct correspondence to the yield in the signal region. That's why we do this trick. So I can force the signal yield to 1 with this helper function, and then I can print this result so you can actually see that I constructed this dummy signal inside there, that this give me 0 events in the control region, 1 event in the signal region, and I will go and fit this thing. Here I'm going to use another function from pyhf. It's called upper limits. I don't think I'm using the latest version of pyhf here, to be honest. So maybe some of these things have been changed and you have a better interface. I don't know. I'm not using the latest version.
Looks like the recent version.
Yeah.
Yeah.
Anyways, it's running. So so what I'm gonna do here, is I get this dummy signal, and I'm gonna start testing different values of new signal. I will start with 1. What's the CLS for 1? Then I will go to 2. What's the CLS for 2? 3. What's the CLS for 3? And then I'm going to find the value of new signal that brings CLS to 0.05. And I define the search space. So I will go up to 30. And I will try 30 values in there. And the value of new signal that gives me CLS 0.05 is what we call observed upper limit, right? So I can run this cell. It's going to take a couple of seconds because it's searching in this space. And this is the observed. For the expected, we kind of need to do the same thing. We need to do a background only. We need to remove signal, do a background only fit, and then use the result of this background only fit as observations to calculate the expected limits. So I can let it do this work as well. And then that's the final bit of information we usually quote in our papers. This is called discovery significance. And this is a measurement of how much my observation follow the background only hypothesis, right? It's kind of a probability to tell you that, I can print this thing, and the probability is 0.06. So it's quite low, right? That my yield follows the background only hypothesis. And anyways, I have printed also here the upper limits And it's maybe nicer if you can, if you see the visualization of this, that it's exactly this, what I was talking about, scanning the new signal to find where the new signal give you CLS value at 0.05, at expected is at 7. So this means 7 events because there is a direct correspondence between the new factor and the yield, and observe is 12. And that's my last cell. I was rushing a little bit to make everything. I did 25 minutes, so thank you for the 5 minutes. As I said, there is a lot. This is gonna stay there in the notebook, and people, of course, you can ask me whatever you want. Alex helped me a lot to put this together, so I thank him back. Yeah, that was it for me. Thank you, guys.
Yeah. Oh, thank you, Vangelis. That was really, really nice. I also like all the additional visualizations. I think those are great. Okay, so this is kind of the end of the morning session, but I still want to make sure that we give some time for questions to Vangelis. So do we have it? If people on Zoom have questions, please raise your hand. Okay, I don't see any, so maybe we can go to the room next.
So I was wondering, when you do these different fits, I mean, wouldn't it be easier to have one configuration file where you can like switch between modes?
Yeah, probably I could take this largest configuration file that has everything, all the backgrounds, all the signal. Maybe I can add here all the regions, and then I can do pruning. I can have one configuration file, and I can create different ways. Even I can do one workspace and then prune from that, right? I can do this thing, yes. I put them like this for clarity mainly, just to show around. And when I start developing this, for me, it was also more clear to have them separated. So there is not big, very important reason. Yeah, you can measure all these things.
Oh, actually, I have your hand up.
Yeah, this is a small thing. When you did your pruning and renaming, I think you use like a internal API, like it's like workspace.underline rename and prune, something like this. Prune and rename, right? I was wondering, can we use existing non-private? I mean, can we use an API without an underline in the name? Do we need this one? Just to ask essentially,
I think there is one which is copy. I'm not. So there is. Yeah, I need to look at the API because I forget. There is one. I'm not sure if this one that you can prune, rename, and copy at the same time. And this is what I was trying to use. Probably it's this one. That's why I use this one, because you can do everything. Now, if there is what is this one?
You can just use the prune function since you're not going to.
Yeah, but I don't think the prune is copying. The prune, yeah.
This prune will not modify the original workspace.
So the prune function, the rename function are all wrapped around the internal, but we just provide a quick function to separate it out. But it does copy.
Okay. Yeah. Then probably, yeah, you can. I think above I use the prune, right? Yeah, I played around with these things here and there, so not everything could be like best.
Yeah, no. I was just curious. Yeah, okay.